Hello everyone, this is Professor DePaulo. Welcome back to Psych 220 Behavioral Statistics. And today I'm going to be talking about analysis of variance, or ANOVA. So the long way of saying is analysis of variance. We typically say ANOVA. And more specifically, we're going to look at what is called the omnibus. It's supposed to be an asterisk. Omnibus ANOVA, or sometimes called the One Way ANOVA. So what kind of ANOVA is this? Well, for this ANOVA, we have one dependent variable, continuous. So a continuous dependent variable, whatever we're measuring, it's continuous. And we have one factor or independent variable. And this independent variable has 3+ levels or groups. And these 3+ levels or groups are all independent of each other. So this is the extension of the independent groups t-test. So the independent groups t-test looks at two independent groups and compares them. The one-way ANOVA looks at three independent groups and compares them. However, we can't directly compare three means because it's kind of awkward. You know, we can compare two means very easily, but three is kind of difficult. So let's say we have three groups, A, B, and C. We can compare them two at a time, right? We can compare A and B. We can compare A to C. We can compare B to C, right? So there's three, basically three two-way tests or three t-tests, right? The problem with running three t-tests is for every test I run, I increase my alpha, right? So alpha is probability of a type 1 error. And usually it stays at 0.05. So 0.05 usually, right? But if I run more than one test, this gets compounded, right? So this increases, and then we have to look at something called family-wise error rate. So the family-wise error rate goes up. It increases as the number of comparisons increases. So it becomes difficult just to run multiple t-tests, t-test A and B, t-test A and C, t-test B and C, because now we're running three t-tests. That family-wise error rate. So the family-wise error rate is the total probability of making at least one type 1 error. And that family-wise error rate goes up, and so we have a greater chance of making a type 1 error if we keep running these, tests two at a time, these t-tests. So instead, we combine everything into an ANOVA, and that decreases the family-wise error rate because we're only looking at 0.05 rather than 0.05 for each of these three tests, which becomes not 0.15, but it becomes close to that. So we want to make our lives easier by keeping the family-wise error rate down. So that comes with the idea of ANOVA. ANOVA keeps our family-wise error rate down. So what does the hypotheses look for like for ANOVA? Well, the null says that the means of the three groups or more groups, right, are equal. The alternative says that these means are not equal. So that tilde means not. So basically, these three means are not equal to each other. Not mu1 equals mu2 equals mu3. So when we reject the null and we support the alternative, what we're saying is the means are not all the same. The groups are not all the same. The null is the groups are all the same. The alternative is the groups are not all the same. And that's all we can say. So when we reject the null, that's all we can say is that 3 groups are not the same, 4 groups, however many groups you have. And the problem with having too many groups is it becomes very difficult to interpret. So if you have 5 groups and you reject the null, you say the 5 groups are not the same. What does that really tell you? It doesn't really tell you much. Now you have to, do the individual comparisons. So after rejecting the null for ANOVA, must run post hoc tests. These are comparisons like t-tests, except their alpha levels, the type 1 error rates for these post hoc tests, is controllable. So the family-wise error rate can stay under control because we adjust the alpha level when we run these post hoc tests. And we're going to be running these, and we're going to be focusing on the Tukey HSD test, honestly significant difference test. And so once I reject the null, I would run these Tukey comparisons, basically. Tukey post hoc tests, technically they're called. They're like t-tests where I compare 2 groups at a time. So I compare group 1 and group 2, group 1 and group 3, and then group 2 and group 3. And I compare to see if they're similar or different. So they're like t-tests, except that their alpha values are controlled. So the alpha values are a little bit lowered to control the family-wise error rate. So reject null, run post hoc tests like Tukey. Fail to reject null, you're done. So if you fail to reject null, you just say that there is no difference. So there's no point looking for differences with Tukey tests because you're basically saying all the means are the same. So fail to reject null, stop, and conclude there are no differences. So that's basically how the ANOVA works. The goal is to reject the null, then we say that the means are not the same. And once we reject the null, we can run our post hoc tests, like the Tukey HSD, honestly significance difference test. We can tell which groups are the same and which groups are different. If we fail to reject the null, we conclude all the groups are the same. There are no differences. So how does this work computationally? Well, it's not difficult. There are just a few different things, and you have to map them out step by step when you're running something like this computationally. So let's take a look at a problem, and then we're going to go through the steps to run the computations. So I'm going to go back to worksheets, which is under table of contents. I'm going to click the ANOVA, and we're going to look at this first problem. See if I can copy it into the okay, we'll see if it stays that way. And it doesn't. Okay. Like everything else, the formatting is always an issue. So we're going to try to fix the formatting. It looks like it's going to be hard. Okay, so let's delete that. And let's try to just copy the problem in. So it looks like it doesn't want me to copy everything into the whiteboard, which is always, there's always a problem with the whiteboard. I wish there was a whiteboard that worked perfectly, but there isn't. Okay, so assume you are a nutritionist who's been asked to determine whether there's a difference in sugar content among the 3 leading brands of breakfast cereal, brands A, B, and C. So to assess the amount of sugar in the cereals, you randomly sample 6 packages of each brand and chemically determine their sugar content. Okay, so we're going to start by copying the data down. So we have cereal brand A. And this is the sugar content in cereal A. Then we have cereal B. And then we have cereal C. So I'm going to start with the hypotheses first, because those can be done without looking at the data. Now the thing with ANOVA is that, and let's scroll up for a bit. ANOVA is positively skewed distribution. So it looks like this. The tail is to the right. The mean of the distribution is about 1. This is called the F ratio. So this is what the ANOVA or the F ratio distribution looks like. It's positively skewed. There's only one tail here, and that's the tail to the right. So before we had one tail or two tail tests when we were talking about Z or T, we no longer have that with ANOVA because ANOVA doesn't have a left tail. It just has a right tail. So we don't have to worry about one tail, not directional or non-directional. There's only one direction, right? And F is composed of a ratio of 2 variances. So ANOVA, which is represented by F because it was developed by Fisher, so they called it the F distribution, is a ratio of 2 variances. It's the between groups variance and it's the within groups variance. The between groups variance is just what it sounds like. How different are the groups? So we have 3 groups here, A, B, and C, right? How different are they? So how different is A compared to B, A compared to C, B compared to C, right? Are they similar? Or are they spread out? Are the data similar for these 3 groups, or are they spread out? The more spread out they are, the higher the between groups variance. And then we have the within groups variance, which is the individual scores in each condition. How spread out are these 6 scores? In A, 6 scores in B, 6 scores in C. Are they very similar? That means small within groups variance, or are they spread out much more? That would be a large in groups variance. So it's looking at the variation between these 3 conditions, these 3 brands of cereal, divided by the variation within these 3 brands, right? Are people very similar in A, or are they spread out? Same with B, same with C. The goal is to have the maximum distance between these conditions, right? Because that represents the treatment effect, the independent variable. That there's a great spread between groups. That's the effect of the treatment, the independent variable you're manipulating. Versus the within groups variation, which is individual differences. Sometimes that's called the error term. So we want to maximum the between groups variance and minimize the within groups variance. And that gives us the biggest F ratio we can get. So the first thing we do is we have this data out here. I'm going to then add up each of these 3 columns, and that gives me the sums of A, B, and C. We call these T, total. So total of group 1, because this is group 1. We're going to call this 17. We added up. This is total of group 2. Total of group 2 is going to be 33. And then the total of group 3 is 34. Those are our totals, the sums of these. So we call them total 1, total 2, total 3. Now, if I add up these three totals, I get something called the grand total. So the T is the group total, but when I add them up, I get something called G, the grand total. The grand total is equal to these three added together. And that is the total of all the scores, regardless of condition. All the scores in the data set is the grand total. And that adds up to 84. So that's my grand total. Now I'm going to square each of these values. So I'm going to have an a squared, I'm going to have a b squared, and I'm going to have a c squared. Remember variance? Well, we're coming back to variance again. So we're going to square everything to make the variance calculation easier. And there's multiple ways to calculate variance, but we're going to calculate it using the computational way this time. Computational formula, just because it's easier and you don't have to deal with decimals. So we're going to square a, b, and c. And then we're going to add up a, b, and c. So the squared of total 1 is 63. The squared of total 2, so b squared, is going to be 197. And then the squared sum of group C is going to be 206. And then we're going to add them together. And we're going to call this sum of x squared. So sum of all the squared scores is 63 plus 197 plus 206. And that gives me 466. So I have the grand total at 84, and I have the sum of x squared, the sum of all the squared values at 466. I'm going to need those to do the calculations shortly. So let's do the calculation. So now that you've set up the problem, this is exactly how you want to start the problem. And now we're going to go into the formulas to find the between groups variance and the within groups variance. Now there's a few things here that we need to take into account. The sum of squares total, that means the total sum of squares for the whole data set, is equal to the sum of squares between groups plus the sum of squares within groups. We also know that the degrees of freedom total is going to be equal to the degrees of freedom between plus the degrees of freedom within. The degrees of freedom between is going to be equal to k minus 1, where k is the number of conditions, or number of groups. And the degrees of freedom within is going to be equal to n minus k, where k, once again, is the number of conditions or a number of groups. So those are the easy ones to figure out here. So degrees of freedom between here is going to be 3 groups minus 1. It's going to give us 2. And degrees of freedom within is going to be n, which is 1, 2, 3, 4, 5, 6, 18. Minus groups is 3, and that's going to give me 15. So we have that done at the start. Very easy to do that. Those you just plug in. Now the little bit more computationally intensive formulas. So we start with the sum of squares total. The sum of squares total is equal to the sum of x squared minus g, the grand total squared, over n, the total sample size. So sum of x squared we have already, 466 minus g, which is 84. So this becomes 84 squared over n, which is 18. So when we simplify this, we get 466 minus 392. That gives me 74. So the sum of squares total is 74. So that's a measure of total variability in the entire data set, regardless of condition. And remember, sum of squares total is equal to between plus within. So if I have total, I only need one more of these, right? So if I have 74 here for total, all I have to do is find the within. And if I subtract the within from the total, I get the between. So I don't have to calculate all three of these. I only need to calculate 2 out of the 3. So I'm going to calculate the total, and I'm going to calculate the within group sum of squares. And then I'll subtract, and I get the between groups sum of squares. Because that just cuts down on the computation. So that's total. Let's do within groups. Sum of squares within is basically the sum of squares in group A plus the sum of squares in group B plus the sum of squares in group C. That's what it is. So we have to do them individually. So it's sum of squares for group 1 plus sum of squares for group 2 plus sum of squares for group 3. And if I had group 4, it'd be sum of squares of group 4. So the sum of squares of group 1 is going to be this value here, 63. So remember the sum of squares computational formula? It looked like this. The sum of x squared minus the sum of x quantity squared over n. That was the sum of squares that the computational formula we did at the beginning of the course. So all I have to do is take this and plug in what I have here for A and then repeat it for B and C. So if I just tweak this a little bit to fit for group 1, it's going to look slightly differently. So what I'm going to have here is sum of squares within is equal to the sum of the squared values for A, which is 63, minus the total for A here, which is 17. 17 squared over the number of people, or number of boxes here, actually. Number of items in group A. 1, 2, 3, 4, 5, 6. This is 17 squared over 6. And then we're going to do group 2. It's going to be 197 minus 33 squared over 6. That's squared, by the way. And then for group 3, it's going to be 206 minus 34 squared. So it looks like a lot of work, but it's really not, because it's 3 things we've done before. We've done variance before. So we're just going to break down each part. So let's do the first part here. 63 minus 17 squared over 6. When I simplify that, I get 14.83. And then we do the next one, 197 minus 33 squared over 6. This is where your squared function on your calculator is going to make your life easier. You're going to do 33 squared over 6, get an answer for that, subtract 197 minus that answer, and I get 155. And then you're going to do it here again, 34 squared over 6, subtract that value from 206, and you get 13.33, rounded. I then add all those values up. And when I add all those values up, I get 43.66 for my sum of squares within. Now I'm really progressing here. I have sum of squares total of 74. Sum of squares within, 43.66. So if I take the within and I subtract from the total, I get the between, right? So sum of squares between is equal to sum of squares total minus sum of squares within. So I have 74 for total. I have 43.66 for within. So the sum of squares between is just the difference of that. And that's going to give me 30.34. That's my sum of squares between. So I'm almost done. I've got the between groups sum of squares, the within groups sum of squares, but I need an average. I need the average between groups variance and the average within groups variance. So remember when we found the variance, we did s squared is the sum of squares, right? Divided by n minus 1. While n minus 1 was the degrees of freedom. So we're going to do the sum of squares over the degrees of freedom for both between and within. The degrees of freedom change depending on if you're doing the between groups or the within group sum of squares. Right? But we're doing the same concept, sum of squares over degrees of freedom. And that's going to give us a measure of variance. Between groups variance and within groups variance. So it's a little bit different than what you see here, but it's the same concept, completely the same concept. So what do we call it now? We're not calling it s squared. We're going to call it the mean squares between. MSB, mean squares between. This is like the average between groups variance. That's equal to the sum of squares between over the degrees of freedom between. So our sum of squares between we have at 30.34. And our degrees of freedom between we have at 2. When I solve that, I get 15.17 as my mean squares between. So I need that. And then I'm going to have the mean squares within, the average within groups variance, which is the sum of squares within over the degrees of freedom within. Sum of squares within is going to be 43.66. Degrees of freedom within is going to be n minus k, which is 15. We did this at the beginning. 43.66 over 15. When I do that division, I get 2.91. And then the last step, which is the F ratio, is the mean squares between over the mean. So the average between groups variance and the average within groups variance. So I just put these two values. And it looks like between is much higher than within, which is what you want. And when I solve this, I get 5.21 as my F ratio. Now, I don't know if that's significant. I have to compare it to the critical value of F. So we need to find the critical value of F from the table again. So to get the critical value of F, I need my degrees of freedom between, I need my degrees of freedom within. So I need 2/15 to find the critical value. So let's go look at the table of critical values. So I have right here. So this is table B4 of the text, the F distribution. You see how the F ratio is positively skewed? There's only one tail. The light face, the regular faced font is 0.05 critical value. The bold faced font is 0.01 critical value. So the regular type is 0.05, the bold type is 0.01. So we have two, so it says degrees of freedom numerator, that's between groups. So I have 2 between, so I look at 2 on the top, and degrees of freedom denominator is within groups. So I have 2 between and I have 15 within. So I find 2 and then I find 15. The column 2 and 15 the row. And if I'm doing 0.05, which I am, I'm looking at the regular font, gives me a critical value of 3.68. So 2 for the column for the between groups degrees of freedom, 15 for the rows for the within groups degrees of freedom, and the regular font for 0.05 gives me 3.68. So I have 3.68 as my critical value from the table. Is 5.21 greater than 3.68? It is. If you want to draw the curve, you can. Here's the curve. It's a positive skew here. 3.68 is here. 5.21 is in the tail. So I reject the null. I've rejected the null, and I conclude that all the groups are not the same. So out of these 3 brands of cereal, they don't have the same sugar content. Under the null hypothesis, in this situation, the 3 cereals have the same sugar content, right? That's the null. When the alternative is the 3 cereals let's say this have here instead of had, because had is past tense. Let's say have. The 3 cereals have the same sugar content. This 3 cereals do not have or you can say they have different sugar content. It doesn't matter. It's just got to be the way I phrased it might have been a little bit awkward. So you could say the 3 cereals have different sugar content. Or do not have the same sugar content, same as different. That doesn't tell you which ones are different from which other ones. It just says they're not all the same. So the 3 cereals do not have the same sugar content. Now that we reject the null and we support the alternative, we have to do, so after rejecting the null, do post hoc tests. So we're going to do the Tukey HSD test. How do we do the Tukey HSD test? Well, there's another table. So the Tukey HSD test now the monitor doesn't want to work for me. Tukey HSD test is going to be Q times the mean squared within divided by N. Q is something called the studentized range statistic. The mean squares within we already calculated here. It's over here at 2.91. And N is the number of participants or objects, in this case objects, in each group. So that's the sample size in each group. This formula assumes that the group sample sizes are equal. They don't have to be equal, but this formula assumes that they're equal. If they're not equal, you're going to use the smallest n, right? But most of the time they are equal. So the number of objects or participants in each group, the sample size basically. The studentized range statistic is sort of a statistical oddity, and there's a table for that. It's called the Q table or the studentized range table. And it looks like the F table, but it's a little bit different. So let's look at the studentized range statistic table. So it's the Q table, table B5. And what we're looking for here is a little bit different. The number of treatments, not the degrees of freedom here. The top here, the columns is number of treatments. So the number of treatments here is 3. So K is 3 here. For the F ratio, we used K minus 1 on top. But for the Q table, we're just going to use K. So we had 3 treatments, and we had 15 degrees of freedom. So we find 3 and we find 15, and we're doing 0.05 because we did 0.05 for F, and we get 3.67. 3.67 is our Q value. So Q is 3.67 here. What does that mean? It's just a number used to calculate. So what we're doing here is we're calculating the minimal distance between two groups for you to say that they are statistically different at the 0.05 level. So this is going to give us the minimum distance between means that would make those means statistically different from each other. So 3.67, so the HSD distance is 3.67 times the square root of 2.91 over n, which in this case was 6. Solving this, which means multiplying this by this quotient, take the square root, we get 2.56 as the minimal. So this is the minimal distance between any two means for us to call them statistically different. So if we have to find the distance between means, we have to actually calculate the means. So let's calculate the means. And I know it's a long problem. It's not a hard problem. It just, there's a lot of steps. So you have to concentrate and do the steps in order. So we need to find the mean of A, which is 17 over 6. So that's 2.83. We need to find the mean of B, which is 33 over 6, which gives us 5.5, and the mean of C. These are our three means. We have to compare them. 34 over 6, which gives us 5.67. Now, the means must be separated by a minimum of 2.56 units for them to be considered significantly different at the 0.05 level. So let's compare them, A and B. So 5.5 minus 2.83, what does that give us? That gives us 2.5, 2.67. So that first difference is 2.67. Is that greater than 2.56? It is. So I put an asterisk there. That means that group A and B are significantly different from each other because this 2.67 distance is greater than the HSD value of 2.56. And then we're going to do A and C. Remember that this is distance, so it's got to be positive. So I do the larger number minus the smaller number, larger mean minus the smaller mean. A and C is going to be 5.67, the larger mean minus the smaller mean, 2.83. And that distance is 2.84. Is 2.84 greater than 2.56? It is. So A and C are also significantly different from each other because 2.84 is greater than the HSD value of 2.56. And then we're going to do B and C. That's the last comparison because there's 3 groups, so there's only 3 comparisons. And then B and C would be 5.67 minus 5.5. That's going to be 0.17. Is 0.17 greater than 2.56? No. So I do not put an asterisk there. There is no significant difference between groups B and C because this value is smaller than the HSD cutoff of 2.56. So there were two significant comparisons. A and B are different. A and C are different, but B and C are not different at the 0.05 level. And you're done with the problem now. Many steps later, you are done. Is it hard? No. Is there a lot of computation? More than there's been, right? But there's nothing new here. This is just plug in the Q value and solve. But for the ANOVA, it's mostly just compute variance. And that's it. So we're just going back to variance again. So that's this example. And we reject the null and we say that group A and B are different and group A and C are different in terms of sugar. And if we look at the mean sugar, group B has, cereal B has more sugar than cereal A. Statistically significant more sugar. And group C has more, statistically significant more sugar than group A. But there's no difference between B and C. So let's take a look at another problem. So this is the back pain study. And we also have 3 groups. Now, you can have more than 3 groups, but more than 3 groups is a lot of computation, so I'm keeping it at 3 groups. Although you can do more than 3 groups, just more variances, right? The following study looks at the effects of ibuprofen on treating back pain. Participants were randomly assigned to receive either placebo, 200 milligrams ibuprofen, or 400 milligrams ibuprofen. The following data are ratings of back pain, with 10 meaning maximum pain. So the null, there is no difference in pain between the groups. So basically, the ibuprofen doesn't work. And the alternative is there is a difference in pain between the groups. So that would signal that some dose of ibuprofen is actually working better than, say, the placebo or a lower dose. Now let's take a look at our 3 groups. We have a placebo group. We have 5 participants in each group. And these are their ratings, and they're quite high. We have a 200 milligram group. And their back pain ratings look better than the placebo group. And then we have a 400 milligrams. Now, personally, that's not a lot. I mean, 200 milligrams is 1 pill, 1 Advil, basically. 400 milligrams is 2. So, if 1 or 2 Advil are making a drastic difference in your pain levels, then you're very, very lucky. Okay, so I have 3 groups. Let's set it up like we did before. So we're going to find our totals, our T1, total of group 1, which is 45. Our total for group 2, which is 25. And our total for group 3, which is 10. We're then going to square these values. And find the totals of those squared values here. 407 for that one. I'm just putting the square. I'm not labeling these. These are just placebo squared, 200 milligrams squared, 400 milligrams squared. That's all it is. I don't need to label it here because we know what it is. Let me add this up. I get 127. And when we add this up, we get 22 for the squared. So I have the totals and I have the squared totals. So this is basically T1. This is T1 squared, T2, T2 squared, T3, T3 squared. I don't have room to write in, T2, T3 squared, T1 squared. There's not enough room here. But that's what it is. Let's do the grand total. Add up the three totals here, the non-squared totals. And my grand total is going to be 80. And then let's find the sum of x squared, which is adding up the three squared totals. And that gives me 556. Now we're ready to plug in. Let's find our degrees of freedom. So this is k minus 1. I have three groups. So degrees of freedom between is 2. Degrees of freedom within, we're going to need them later. N minus k. N is 15, the total sample size. 3 is the number of groups. So those are my degrees of freedom. Now I'm ready to start the problem. That's just setting up the problem. Now I'm ready to start it. So start it with sum of squares total. And it's going to be the sum of x squared minus g squared over n. Capital N is the total sample size. Sum of x squared, we have 556. G, we have at 80. And n is the total sample size is 15. And when I solve that, I get 129.33 as my sum of squares total. Now the next one to do is now I calculate sum of squares within. You could do sum of squares between. So for this one, I'll actually do sum of squares between and sum of squares within. So let me do sum of squares within first. This is the sum of squares for each group. So it's 407 minus 45 squared over 5 plus 127 minus 25 squared over 5 plus 22 minus 10 squared over 5. So simplifying this gives me 2 plus 2 plus 2. Well, that's strange. 2 plus 2 plus 2 gives me 6. So each of these, the sum of squares of each group was 2. That was an odd coincidence, but that happens. 2 plus 2 plus 2 gives me 6. So my sum of squares within is 6. Therefore, my sum of squares between is 129.33 minus 6. My sum of squares between would be 123.33. But we can do the calculation just to show you how to do the calculation for between. So the sum of squares between is going to be equal to the T1 squared value over N1 plus the T2 squared value over N2 plus the T3 squared value over N3, or the sample size of each of the groups, minus G squared over N. So when I simplify this, I get T1 squared, which is 45 squared, right? Over 5 plus 25 squared for T2 over 5 plus for T3 10 squared over 5 minus G squared which is 80 squared over 15. And when I simplify this, I get 405 plus 125 plus 20. And that gives me 530, 550. So these values here gives me 550, these three, right? So this minus g squared over n, which calculates as 426.67. So 550, which is 405, 125, and 20. That's 550. That's these three. Minus this, which is 426.67. And that gives me 123.33. Now, do I have to calculate sum of squares between? I don't. All I have to do is find sum of squares total, sum of squares within, and take sum of squares total minus sum of squares within. That's much easier than doing all three. But if you want to comfort yourself, if you're paranoid about making a mistake, you could calculate sum of squares between and get a value and then add that value to within, and you should get the total. So you don't have to do between, but if you want to, you can. It's just a lot of computation, as you can see. So it's a lot more computation than you need to do. If you've done these two right, you're going to have the between. Just do total minus within, and that gets you between. So now we have those. Let's do our mean squared. So our mean squares between is sum of squares between over degrees of freedom between. So that gives me 123.33 over sum of squares between is 2. Degrees of freedom between is 2, I should say. So that divided by 2 gives me 61.67 mean squares between. And then mean squared within is sum of squares within over df within. That gives me 6 over the degrees of freedom within is 12. That gives me 0.5. That's a really small within groups mean squared. Really, really small. So now I calculated the F ratio as the mean squares between over the mean squares within. So 61.67 over 0.5 gives me a huge value of 123.33. That's massive. So that means there's so much more between groups variability compared to within groups that this is making a huge, the treatment is making a huge difference here. A huge difference. This is going to be significant, but we should find the critical value, even though this is so gigantic that it's going to be significant. Our degrees of freedom are going to be 2 and 12. So let's look at the table for 2 and 12. Just go to F. We're going to find 2 at the top, 2 degrees of freedom between the numerator. 12 is within. And we're looking at 0.01. So we're looking at the bold value now, because the bold value is 0.01. So 2 and 12 gives me 6.93 as the critical value. And that actually means nothing because our value is so big. So is F larger than the critical F? It is, so we reject the null. And we say that the groups are not all the same with regard to back pain. Now we have to do our post hoc tests, since we rejected the null. Must do the Tukey test. or any of the other post hoc tests, but I'm giving you Tukey because I think Tukey's like the fairest one, I think, for finding effects. Some of them are very conservative and very punitive, and Tukey's a pretty liberal test, so that's why I kind of like the Tukey HSD. So we're going to have to plug in here and find our values. So our Tukey HSD, it's Q times the MS within over the sample size of each group. So Q, we have three groups, and we have 12 degrees of freedom within. So we're going to go find that in the Q table, table B5, 3 treatments, 12 within, and we're using 0.01. So we find 3 and 12, and we get 5.05. So 5.05 for our Q. So this is 5.05 times MSW, which is 0.5, over the number of people in each group, which is 5. So when I multiply this out, this is square root, by the way. So it's 5.05 times the square root of 0.5 over 5, which is equal to the square root of 0.1. So this becomes 5.05, and the square root of 0.1 is 0.316, and I multiply that by 0.316, I get 1.596. So the means have to be separated by a minimum of 1.596 for them to be deemed significantly different from each other. So let's find the 3 means. So the mean of the placebo group is 45 over 5, so that mean is 9. The mean of the 200 milligram group is 25 over 5, that mean is 5. And then the mean of the 400 milligram group is 10 over 5, and that mean is 2. So those are our 3 means. Let's do the comparison. Placebo compared to 200 milligrams. It's going to be 9 minus 5 equals 4. Is 4 larger than 1.596? It is. So I put an asterisk. That means it's significantly different. So placebo is significantly different than 200 milligrams of ibuprofen in terms of back pain. Because 4, the difference of means is greater than the minimal difference for Tukey, which is 1.596. And now we do the other 2. Placebo versus 400 milligrams. What are those means? 9 minus 2 is 7. 7 is much bigger than 1.596, so that's different. And the last one is 200 milligrams compared to 400 milligrams. And that difference is 5 minus 2. That gives me 3. Is that bigger than 1.596? It is. So all 3 groups are significantly different than all other groups. So placebo is significantly different than 200 milligrams. Placebo is significantly different than 400 milligrams. And 400 milligrams is significantly different than 200 milligrams. So all 3 groups are significantly different from each other. And the best results are with the 400 milligrams. They have the lowest mean value in terms of pain. But that's different than the 200 milligrams. So that extra 2 Advil or 2 ibuprofen is better than 1. Significantly better than 1. And they're both significantly better than nothing. So the ibuprofen is working great for the back pain. And that's it. And that's how you do the ANOVA and the Tukey post hoc tests. I know that's a lot of computation. It's a lot of work. Hopefully, if you break it down the way I broke it down, you'll be able to solve it pretty easily. It's not difficult. It's just steps. So do the table first, set it up first. Like I set it up like this. Find all the sums, find the grand mean, find the sum of x squared. And then once you do that, work on the sum of squares total, work on the sum of squares within, and then subtract within from total, and you get between. If you have to do between, you can do between. It's just a lot more work. If I reject the null with my f, I then do post hoc tests. If I do not reject the null with f, I do not do the post hoc test because it's not necessary. And that's it in a nutshell. Hopefully that helps. If you have any questions, let me know. If not, I'll see you next time for correlation and regression. Bye for now.